So welcome everyone. Thank you for tuning in for this talk, this UniKORN seminar. We're still doing our first block, which is on the theme of optomechanical interfaces of quantum mechanics and gravity. We're very happy today to have a speaker with us. And just to remind you of the house rules, to be respectful when chatting and talking, please mute your mic and your video during the talk. And we'll take questions after the talk. So if you have them at the end of the talk, please raise your hand and we'll ask you to unmute, or you can write them in the chat. If you're listening on YouTube, please write them in the YouTube chat. We're watching that one and we'll relay them to the speaker. So just to advertise the talk we have next week. So we have some talks by early career researchers. So we have Ryan Marshman, Sandra Donadi, and Matteo Carlesso, who will be speaking to you about the quite recent research results. So please tune in for that one as well. And the session the week after that, so in 2 weeks' time, we have a panel discussion on basically the topic of the block. And we're really excited for that one. We have 6 really experienced people from both from theoretical physics and experimental physics. So we think that that will be really exciting, and more information to follow on that later on. But now I'll just introduce our chair. So thank you so much for chairing Myungshik. And Myungshik is a professor at Imperial College London, and he's working on quantum information and quantum optics. So thank you so much for chairing, and I'll hand over to you.
Thank you very much, Sophia, to chair this session. And thank you very much, Igor, for your agreeing to give a talk here from Sweden, Stockholm. A few years ago, I saw Igor at a small cafe in Providence. And I went there for a demo meeting organized by American Institute or American Physical Society. And what a surprise to see Igor in the land of America. So I thought, wow. And he said he was there to give an invited talk. I went to his session. He gave a talk on the time gravitational time dilation as a cause of universal decoherence. The room was extremely packed. I think it was probably the most popular talk of the event. It was extremely good to see that. Before then, that was not the first time to see him because I was involved in supervision of his PhD at Vienna. So the earlier, so like about 10 years ago, even 12 years ago, I saw Igor in Vienna as a PhD student. That time, Markus Aspermeyer asked me to give a talk in Vienna. So I went there and acknowledging that there are qubit people, I prepared a talk on qubits. And then, so I gave a talk, in my opinion, a good talk in qubits, but there Igor saying, well, he's very much interested in continuous variables. In fact, Marcus invited me to talk with Igor, and we shared the same language. It was extremely good, and we shared some ideas, and out of which he gave extremely nice. The follow-on work, and it was very good. So that was the like pulsed quantum optomechanics, and also the probing Planck scale physics with quantum optics. That was very good. So that's Igor has pioneered many other things to connect the tabletop experiments with the general relativity and gravity. Here we go. Igor, after his PhD in Vienna, went to Harvard with a fellowship, and he spent many years in Harvard and moved to a permanent position in Stephenson Institute. Now he's in a superposition or the statistical mixture of his time in Stephenson Institute in New Jersey and the University of Stockholm in Sweden. So here we go. Igor will give us a talk on optomechanics as a versatile tool to probe classical and quantum gravity. Thank you, Igor. Welcome.
Yeah, thank you very much, Myungshik. That was a that was a very kind introduction, and you know, people always say that, but in this case, that was a very surprising introduction. So thanks a lot. I also remember our first meeting in Vienna a long time ago, and it's been very fruitful and exciting collaboration since. So this is yet another reason I'm actually very excited to give this talk, getting an invitation from you, Henrik, and Sophia in this series. So thank you very much for that opportunity. Let me try to share my screen. Okay, I hope you can see my screen. Okay, I don't see anybody anymore, but if nobody complains, I guess the screen is there. All right, so in this talk, I want to talk about optomechanics as a versatile tool to probe classical and quantum gravity. And so mainly what I wanted to summarize here is that optomechanics can offer many different avenues to probe the interface between gravity and quantum physics. And this is itself a topic that I find very exciting, and it's kind of my main research direction and of my research group. And it's something that has evolved, and I've been working on that, you know, for a while, maybe for 10 years or so. And there's a lot of open questions and new developments and new ideas that are especially now becoming much more active as a field. So thanks also in that regard for inviting me, because this is precisely a topic which is very dear to my research interests. Okay, but first, let me just zoom out and talk very broadly about the interplay between quantum systems and gravity at low energies. So the idea of effects of gravity in low energy quantum mechanics is not, or was at least not very common to study until very recently. And so usually people talk about, especially quantum gravity, but in general, the kind of interface between quantum and gravity, either on a very conceptual level or in the context of high energy phenomena, you know, maybe some scattering experiments, possibly probing things like supersymmetry, or maybe astrophysical observations. But there is actually a very rich and very broad interface at low energy quantum mechanics with gravity. And so here, just to give a very brief overview of the different active research directions. One is where people, and especially experimental groups, are studying simulators and analog systems using quantum optical devices or other tabletop devices that behave very similarly to some effects that we know from general relativity or quantum field theory on curved spacetimes. So examples are such as finding analog systems of Hawking radiation or simulating certain GR metrics that people can study in the laboratory. So it's a very large and very interesting field of research where indeed low energy physics meets gravity through a mapping or analog behavior. Another aspect, a very straightforward one, is that we use quantum optical systems for high precision measurements. And so we leverage the quantum behavior of our systems in order to create measurement tools which are better in some sense, or in some aspects, than classical counterparts. And so these high precision tools could be atomic clocks, it could be just in general quantum sensors, and that we use them in order to just test gravity in new regimes. So this is quantum mechanics coming in as a means to obtain high precision. There's other interesting aspects, especially theoretical ones, which is when we look at quantum effects from a perspective of quantum optics in fields such as cosmology. And one prime example is, in fact, inflation, where at some point in the 90s, it was realized that the effects that inflation has on the quantum fields is that it introduces squeezing, and that we can use our understanding of squeezing from quantum optics in order to better understand what's going on in early inflation. But one can also go beyond that, and this is here just one example of work I did in collaboration with Avi Loeb, where we explored other possible effects that we do know from low energy physics and quantum optics in the context of cosmology. Some speculative model here, for example, is a depiction of Bloch oscillations, which are quantum solutions and have no classical counterpart in the presence of very specific potentials, which may be the case in cosmology as well. And even more philosophically, in some sense, or fundamentally, we can apply quantum information concepts that we understand well at low energies in many body physics as well as deep quantum foundations for a possible better understanding of the role of quantum gravity and where it appears. And so how it might emerge, or maybe even understanding quantization of black holes or other phenomena using quantum information concepts and possible discretization of space-time geometry. So it's a very vast and very exciting field of research that links together these different communities. Okay, and the last two aspects I want to mention are those which are kind of the closest to my research interest, although I do find all of it kind of very exciting. One is to use quantum optical systems and abilities that are given to us through quantum optical experiments to actually test some phenomenological models of quantum gravity. And so this is about the goal to bring experiments into the study of quantum gravity, at least in order to constrain some speculative models. And so that's very similar in spirit to, which is now an active field of research in terms of dark energy or dark matter, where we look at specific experiments that we can build in order to constrain some specific speculative models. Now, these models may or may not be well justified or true, but here the main point is that we can bring experiments in order to answer these questions empirically and not through pure debates. And then finally, which I also find very interesting, is to look at quantum dynamics on curved spacetime, meaning that we use these quantum systems as probes of some behavior where their quantum nature is changed due to the background spacetime. And so this is somewhat analogous to quantum field theory on curved spacetime, where new phenomena can arise. But similarly, even at low energies of our systems of interest, there can be new phenomena that arise. And so this is also an active field of research. And Myungshik briefly mentioned this work on time dilation and how it affects some quantum dynamics of systems such as matter waves or clocks. And so there's many other examples as well. And I think these are very interesting fields to explore. But in this talk, mainly because it is focused exclusively on optomechanical systems, I will specifically talk about mostly about quantum gravity phenomenology. So this part which is here on the bottom right corner. And the reason I don't want to talk here about this time dilation work, it's a different work, but also I don't have a good idea how that can be linked to optomechanical systems. But other systems are better suited for it. Okay, so this is just kind of an overview from above, how in general low energy physics meets gravity. So the outline of this talk is that first I want to just talk a little bit about some aspects of the interplay between optomechanics and gravity and what kind of different directions they are. And then I'll give a couple of examples. One is testing gravitational collapse of the wave function with optomechanical systems, which is historically, I think, very important for the development of the field. And then I'll very briefly say a few words about gravitational wave detection with superfluid helium optomechanics. And then finally, in the second half of the talk, I'll focus on testing models of quantum gravity that have so-called commutator deformations. And so I'll show the type of optomechanical scheme that we proposed and developed together with Myungshik as well to probe such models. And then in the end, I'll speak a bit about challenges, experimental developments, and other theoretical insights since then. Okay. So first, just a few words on optomechanics. It doesn't really need introduction probably to most people in this audience, but it's a very specific quantum optical system, which is very interesting. And so in just very brief words, for those that haven't encountered it yet, optomechanics is about the interaction of a mechanical resonator, which interacts with a radiation field. And so a typical example is light interacting with a small mechanical mirror. And so it could look like that. If you have light trapped in a cavity and one end mirror is movable, so it's a small mirror which can be displaced, then through radiation pressure, the light pushes the mechanical resonator into a different position. And so it's basically having like a little solar sail inside your tabletop experiment, and you'll shine laser on it. But there is a back action as well from the mechanics onto the light, namely the frequency of the light inside the cavity depends on the length. And so as the system is being displaced, the length changes, and that changes in turn the frequency of the light. So there's a coupling between effectively two harmonic oscillators. One is the mechanics in blue, one is the light, which are the modes inside the cavity. And then there's a coupling between the number of photons and the position of the mechanics. So this changes the phase of the light, and it imparts a momentum on the mechanical system. So this is just in a nutshell, kind of at the core of optomechanics. Now, it's a very versatile tool because not only do we have many different experimental realizations and different variations of this type of systems and Hamiltonians, but it also ranges across very vastly different scales. If you just take the mass scale alone, it goes all the way from picogram systems, where you have these kind of small waveguides, all the way up to Ligo mirrors in the gravitational wave detectors, which weigh a kilogram. And so there's a huge variety of different systems which people are studying and different geometries of it. And it also spans a wide range of mass scales. So it's very exciting because you can start probing quantum physics at scales which were even until recently unthinkable to be reachable with quantum systems or quantum measurements. Okay, but that opens the route to study some fundamental physics. So I'm not even talking about all the applications, which are very exciting, and there's many interesting aspects of it, where I think there will be another lecture series this semester in this society. But here, just focusing even just the fundamental questions that arise having such a system. So we have a versatile tool. We can do full quantum control over these systems, ideally, meaning that we can change quantum states with ancillary systems. We can do high precision readout, and we're accessing new physical regimes. So some of the questions are such as, is quantum mechanics valid in the macroscopic realm? So now we're talking about kilogram mirrors or other mass scales and length scales. Is quantum mechanics valid there, and can we probe it? Are there signatures of the quantum nature of gravity? So we're talking about massive systems now, maybe not stars, but still more massive than atoms. And so gravity may start to play a role. And indeed, we now know that this is, of course, the case, and there are very exciting proposals. Can specific quantum gravity models be constrained? So do we have some predictions from maybe some of these models? We don't have a full theory, but are there some things that we can probe which go beyond physics as we know it? And finally, can we design novel instruments to test gravity, some Earth-based instruments that serve as tests? And so these are the different questions that optomechanics addresses, and there's different proposals, a vast range of them, and also experiments. And so here, just a small kind of my attempt to classify things somewhat, to give some example. So on the one hand, we have systems as precision measurements, precision instruments. That means that we use optomechanical systems in order to gain very precise measurements of something else of interest. And so one example is to use them for gravitational wave detection. Obviously, the canonical example of optomechanics is Ligo, where it's relevant, and so that is used for gravitational wave detection. And there's other ideas in this direction, and here's, for example, one where one uses optomechanics for a different type of detector. Or here, a different example where it's the measurement of big G. So big G is the fundamental constant in nature, and one that is the least constrained by experiments. So it's very hard to actually measure big G, because usually also the mass of the system or the density of the system comes in as well. So it's easy to measure little g, but hard to measure big G, because often we just don't know the masses involved. It's a weak force, and so we need large masses, and then there's a lot of room for uncertainty. But there are some exciting proposals in order to do that precisely with optomechanics. Now, another aspect of these systems is to try and probe the quantum character of systems. So one example is whether there's macroscopic realism and violations thereof in these macroscopic systems from this. And then, of course, the very well-known and very influential proposal from recent years, the test of quantized gravity. So we're probing some quantum character in new regimes, and here it will be the quantum character of the source masses and how they gravitate with each other. So that's the famous proposal by Bose, Myungshik, Hendrik as well, and Jared Milburn and others from 2017, as well as Vlatko Vedral. In this talk, I won't speak about it, not because of lack of interest, but also because we had a very beautiful talk from Mauro Paternoster last week, and I think there will be more on this topic in the upcoming sessions. Okay, and then the final category is where we can use the system to probe some new speculative physics. So that's physics where which may or may not be there, but it's some kind of model, something like beyond standard model ideas that where physics could be different. And one example is the collapse of the wave function induced by gravity. Mainly the idea that maybe quantum unitarity and quantum dynamics ceases to be correct at certain mass scales. And then another example is where you have some quantum gravity predictions that the Heisenberg uncertainty relation might be violated at some scale, and that you can have experiments to try and constrain or test such ideas. Okay. So here I want to talk a little bit about different topics, and mainly second half focus on this canonical commutator deformations. But first, let me say a few words about this gravitational wave function collapse and how optomechanics fits the picture. Okay, so the main question is, does gravity destroy unitarity? And why should it destroy unitarity? It's a good question if this may take place, and there is speculation mainly by Roger Penrose, he's the main proponent of it, that gravity might be responsible for the breakdown of quantum dynamics at some scale. The basic argument is the following, just to summarize it. If we have a massive object that we input in superposition, we also at some point have to include its own gravitational field that the system is creating. So if you create an object like the Earth to be in superposition of two different positions, you're also at the same time creating two spacetimes, which should coherently be in two different superpositions. Now, what does it mean to have two different spacetimes in superposition? That's an interesting question, and one can probe. And in Penrose's argument, there's a problem that arises because quantum dynamics is defined with respect to some time evolution. The time evolution itself is not independent of the metric, and so the notion even of having something evolving in time would depend on what type of metric we choose to assign to the system. But now we have a superposition of two different distinct metrics. And in theory, these metrics could be completely different, not just displaced, but it could be one is a black hole and the other is something completely different. So what does it even mean to have one and the same time evolution? And so, at least in Penrose's argument, you would need one and the same time evolution. And so because we cannot kind of make a mapping between these two different spacetimes, they're two distinct ones, his postulate is that there is no time evolution. There is some kind of intrinsic fuzziness of the time evolution involved because there's no individual metric that we can define. And so this is the postulate that there's some effect on the unitary evolution of superposition and that have some intrinsic error. Now, one can try to put some quantitative arguments there, and this is what he tries to do. So his postulate is that there is some effective self-energy of the system, as it is in superposition, self-energy that quantifies how much it's affecting the other spacetime, or I mean the spacetime of itself in a different position. And the self-energy depends on this mass densities of the system of two different positions. And so from that, one can define a time scale, which is postulated to be some kind of time scale where unitarity, or this normal evolution with respect to a single time, breaks down. And so this is a speculative suggestion. It's an interesting thing to consider, but in most, of course, theories of quantum gravity, this problem does not arise, and you get some kind of entangled state of different time evolutions. But Penrose's suggestion is that indeed there is some breakdown because of some intrinsic problems with the notion of time. Okay, so the most exciting thing about it is that it's actually experimentally testable. So you have a specific time scale at which your superposition should break down, and this time scale is accessible in experiments. In particular, this becomes significant around masses on the order of nanogram. And this is how optomechanics comes in. And so there was a proposal long ago, even in the late 90s already, to try and use optomechanical systems to probe this particular model. And so at least in my knowledge, this is the first application of optomechanics to some gravity or quantum gravity ideas. And I think it was very exciting and very influential because it showed that you can actually do something at low energies, something meaningful, and test something without needing to go into black holes or think about other type of unreachable high energy experiments. And so the first proposals were by Sugato Bose, Kurt Jacobs, and Peter Knight. And then it was a more concrete proposal by Marshall, Simon, Penrose, and Baumeister in 2003. And so just very briefly to summarize that, the idea is to use optomechanics that is interacting with just a single photon. And so the idea is that you have a single photon that enters and is split to go between two different paths. In one path, you have a stationary cavity, which is just a reference cavity. And in the other path, you have also a cavity, but there the end mirror is replaced by these optomechanical systems that can be displaced. So your initial state is the photon in red to be in superposition of 0 or 1 photon in each mode. So here we only look at the mode in this particular optomechanical cavity. And the mechanical mirror is in some initial, say, coherent state. Could also be a thermal state. But then after some time, because of the evolution, if there's no photon, then the mirror evolves freely. But if there's a photon, then there's also on top of that a displacement from a single photon. So we're talking a single photon displacement of a mirror, meaning that it has to be a very high finesse cavity, such that the photon can have many bounces in order to displace the mirror significantly. And so this kappa is this coupling rate of a single photon, which directly depends on the finesse. Okay, so basically what we're talking about is that you have this state of the mirror, which is periodically displaced by the photon, but this displacement also depends on the mechanical frequency, the free mechanical frequency of the system. And so if you look at the time evolution here in terms of a Wigner function, then you see that it's split into two different superpositions with these characteristic interference patterns. And at certain times, you have a revival where the system disentangles again. Okay. And so what happens is that after a while, some random time, the photon will leak out from the cavity, depending on the cavity decay rate. The same goes from the stationary cavity if they have the same decay rate, and you interfere the photon. Now, the interference of the photon here given by the visibility is actually a measure of how much entanglement you had with the mechanical mirror. So initially you see full interference, and after a while the interference drops because the mechanics is actually measuring where the photon went. If the mechanics is sufficiently displaced, you know that the photon was in this cavity and not in the other one. So there's no interference, but mainly there is a revival. And this revival is an indication of the fact that after a while, the system disentangles again and it remains coherent. And so you get this revival if there's no leakage of this information where the photon was into the outside world. And so it's this revival which is crucial here in order as a signature of the quantum nature of this mechanical resonator. So you get this displacement which is strong enough so that you can really distinguish the two states, displaced and not displaced, if this coupling rate is strong enough. So a single photon needs to displace it sufficiently. And that's, of course, hard, but that's what's needed. Okay, and so this revival drops if you have some kind of loss of coherence. And that could be either due to the Penrose collapse, which would be the signature of it, or it could be other deleterious effects, of course. And so we looked at, when I joined this type of project, we looked at different channels of decoherence and compare them to Penrose collapse, and just to see what the time scale is and how they scale. And there's, of course, many, many channels of decoherence of such a system that one can look at. And one can then compare to what you need in order to see the Penrose collapse or rule it out. It is easier, of course, to rule it out than to see it, because to rule it out, you just need to see full revival, and then you know nothing decoherent. And the opposite is harder. If you see decoherence, well, could be Penrose, could be other things, so you have to be a bit more careful. Okay, and so like I said, it's masked by decoherence. And if you get like an estimate of this Penrose collapse, it turns out that this, even though this model is kind of well defined quantitatively here, it actually has a lot of intrinsic ambiguity in the sense of that it's not clear what this self energy is with respect to the mass distribution. So you have actually a free parameter in this model that you can constrain, and you have to constrain because you have to assume how the mass is distributed. Because if you distribute the mass too narrowly, then this self-energy explodes even by itself, and that is already ruled out. And so there's a question of, what mass densities do you have to put at? Is it individual atoms? Is it individual nuclei? Is it a wave function extension, and so forth? And so you have a free parameter, and then depending what you plug in, you get different time scales for this coherence, like on the order of between a millisecond and a second. So the point is, this is now, the proposal is nearly 20 years old, and my work here is also very old. And this experiment still hasn't been done. I know the Baumeister group is working on it, and many other groups as well in different variations of this proposal. There's no experiment today that can probe it interferometrically. And since then, there have been many alternative tests that were proposed, which are so-called non-interferometric tests. And so what they rely on is that this Penrose collapse, in order to incorporate that into quantum mechanics as we know it, that one can do it in terms of some open systems model, and that's done by Diyoshi. And if you do that, then you have also other side effects that have nothing to do with the coherence per se, but have to do with the diffusion and anomalous heating that come out of it. And so you can actually probe these side effects easier than the superposition. And there's very beautiful constraints and recent experiments on that, including just this year or a few months ago. Okay, so this is just to say a few words on this class of problems, also because I think they were extremely influential to not just optomechanics and its interest as a device for fundamental physics, but also in sparking the interest in studying the interface between gravity and quantum physics at low energies, especially with such systems, because it showed that there's actually some things that we can do. Okay, and now let me just shift gears and just very briefly talk about a more recent proposal that we had with my collaborators, Keith Schwab, Swati Singh, and Laura Di Lorenzo, where we just showed that you can also use it as a novel type of high precision tool for some interesting gravitational physics. Okay, so what we showed is that you can have a different type of gravitational wave detector than what is currently operational. And so just as a very brief summary, I think you're probably most all aware, gravitational waves are solutions to Einstein's vacuum equation, and they propagate in space at the speed of light. And what they do is that perpendicular to their propagation, they change the effective distances between neighboring particles. And so this is described by the metric where h is the perturbation due to a gravitational wave. And so it changes periodically the distance between separate points if we measure them, say by any kind of probe that measures them, even though they're at rest. So I think that's a special thing. Systems are completely at rest with respect to each other, and yet their distance change. So there's two different type of classes of detection scheme. One is to use resonant bar detectors, and it really started the entire experimental business of gravitational wave detection with Weber bars. And that's stretching of a material because there's an effective tidal force acting on the system. So as you stretch the system and you have atoms inside of it, one can show that it's just an effective tidal force acting on it, and then you get phonons that are excited. And so you can resonantly they're resonantly excited, and so you can try to detect them. Or you can have free space detectors where you measure distances with light, and this is the, of course, Ligo operation, and this has been very successful. Okay, so the Ligo principle is when you have optical interferometry. So in fact, you also have optomechanics here because the gravitational wave changes the length of these cavities, and then you look at the phase shift of the light. Okay, and so just as a very brief primer, if you have like a specific distance from A to B between two systems, and then the gravitational wave comes down to it, and you have light going from A to B, you can look at the null geodesic and the solution to that, and so one can just compute it where h is due to this gravitational wave. And then if you have a very small distances compared to the gravitational wavelength, then you get this famous Ligo signal, which is a fractional strain sensitivity, which is directly proportional to the strength of the gravitational wave. So the change in the distances divided by overall distance is imprinted on the phase of the light, and that gives you information about the gravitational wave. And so obviously optomechanics has been fundamental for LIGO, and vice versa. LIGO was actually, I think, really the first starting point of studying optomechanics. Sorry, was there a question or? No, okay. So LIGO was the starting point of studying quantum nature of the mechanics and the noise induced for it. And so you need to look at classical radiation pressure noise, quantum back action noise, and different optimization schemes that rely on quantum mechanics, especially also quantum mechanics of the light interacting with the system. And so that's a very exciting aspect of optomechanics as well. And you get the sensitivity curves where you can play around with it using quantum aspects of light. But here, just to briefly mention, is what we looked at is just a different type of optomechanical sensor, namely a bar, exactly the same as a bar detector. So there's nothing fundamentally different, except for this bar detector is not just simply kind of an aluminum sphere or cylinder, but instead it's a cylinder which is a small one on a meter scale or less, which is filled with helium, and namely is filled with superfluid helium. And around it is a superconducting microwave cavity. And what you do is you put it as part of a LC circuit for microwaves. And what happens is that the microwaves, you have this cavity for these microwaves, but the superfluid helium changes the dielectric constant of the system. And if the superfluid helium has any phonons which are excited, which is precisely this perturbative tidal force which acts on them, either due to by hand, you can just shake it, or due to a gravitational wave, as you excite phonons, it will change the dielectric constant inside the material. And so that imprints a phase shift on the microwaves. So it's exactly just a optomechanical principle. You see a phase shift on the microwaves, from this standing wave cavity. And so you can look at different modes of this system, and what matters is the quadrupole moment of the system. That's directly what's coupling to the gravitational wave. And so you can look at different modes and acoustic modes, fundamental modes, and other modes, and find which quadrupole moment is kind of best suited. And then what you can show is that you can actually get a detector. So now it's just about playing with numbers. You can actually get a detector which could be comparable to LIGO sensitivity in the particular frequency range, which are the fundamental frequencies of such a superfluid helium resonator. So the main aspect is it has a very high Q factor, so you can average the signal over extremely long times. So we are talking about Q factors bigger than 10 to the 8, which is what the Schwab group is aiming for. It's a small detector, so you can kind of easily implement it. And one very interesting aspect of it is tunable. So this detector, when you pressurize the system a little bit, so you change the pressure inside of it, you also change where these fundamental modes lie. So you change their frequencies. And so by pressurizing the system, you can tune your narrowband detector, because this is a resonant detector. It's narrowband as opposed to LIGO, but you can tune where you want to go. And the reason why this is interesting is because it operates in the kilohertz range, just because of the frequencies of the detector. And in the kilohertz range, there is actually interesting gravitational wave physics, which is related to continuous sources. So LIGO has these sources, which are black hole mergers at the very end stage of their life, which are very faint signals and very short-lived, milliseconds or seconds. Whereas here, if you have pulsars, neutron stars, which are rotating at a certain frequency, they may emit gravitational waves over, continuously over a very, very, very long time span, hundreds of thousands of years. They're well suited for a detector which needs to accumulate a signal for a long time. And the reason pulsars may emit gravitational waves is because they might not be perfectly spherically symmetric. And so they have some shape deformations, so they will for sure lose energy due to gravitational waves, but we don't know how much. So there's not just enough that we know about neutron stars to know how much they do emit gravitational waves. And so there are limits from LIGO, and we can compare it for these type of theoretical detectors. And we can see that it's comparable or can in some cases also be better than these systems. And so just to give an overview, we're talking about this frequency range here, kilohertz. And so this black curve here is the kind of the LIGO band. And this is roughly the case for these theoretical numbers. And so you can tune your detector to different sources. And there's tons of different neutron stars that one can tune to and try to detect it. And so it can place limits or maybe even detect gravitational waves from them if indeed they are as strong as they could be, but we don't know. Okay, so now finally, in the last half, or I don't know how long I have, maybe 20 minutes or so of the talk, I want to shift gears for the second time and talk about a different type of proposal, namely using optomechanical systems in order to constrain some quantum gravity models under certain assumptions. Okay. So the type of models that we're considering here are so-called modified uncertainty relations. So obviously, there's no complete theory of quantum gravity. So we don't know, there's many competing theories, but also none of them is complete in the sense that we even know the full mathematical structure, let alone can derive experimental signatures which are bulletproof. Still, there are some concrete predictions that many of these models actually give and one can derive. Among them is one of the relatively universal, interestingly, relatively universal prediction that it's very likely that the Heisenberg uncertainty relation is violated at some point, or not violated, is replaced by some more stringent uncertainty relation at some scale. And so this modified uncertainty relation is pretty common to many approaches to quantum gravity. And I think the first time it was actually derived was from within string theory. So it's one of the few kind of predictions of string theory or scattering of strings at some length scale. And so these are, it's an old result, and it also appears in many other models. And a typical form of this changed modified uncertainty relation is that delta x times delta p is not just simply bigger than h bar half, but it also has a small correction which scales with momentum squared divided by the Planck momentum squared. And so just to give you a picture to get a feel for what this means, what you see here is the minimal uncertainty curve for the normal quantum mechanics, that's in red. And so what that means is that all states to the right of this curve are allowed by quantum mechanics. And obviously we cannot have states which have smaller uncertainty that violate the uncertainty principle due to Heisenberg. And now this quantum gravity modification, it modifies and even reduces the state space even further, namely at a kind of momenta and position uncertainties, which are kind of far out here where experiments currently are, and there's no real difference between these two curves. But if you come close to some characteristic length scale, namely this length scale, which is governed by this free parameter beta naught, then there's a drastic difference between the Heisenberg uncertainty relation and the generalist one, namely it doesn't go to zero, so there's a gap here. And so there's a minimal position uncertainty, which appears in this theory, and it's not possible to prepare or measure states lower than this position uncertainty. And so this position uncertainty is actually the Planck length times the square root of this beta naught parameter. So in other words, this beta naught parameter simply parameterizes where there's some effective cutoff of our notion of kind of continuity of position. So what it basically tells us is there is, physically, it doesn't make sense to have position eigenstates in your theory. They have infinite energy. And so you have to deal with some kind of effectively smeared states always. And so there's some intrinsic uncertainty that you can never get rid of, no matter how much you increase uncertainty in delta p. And so this is just characterized by a free parameter beta naught. And of course, from string theory in their calculations, they didn't have this free parameter, they had some characteristic length scale, it's an order 1. So it's kind of expected to be close to the Planck scale where this minimum uncertainty is, but it could be any number. Okay, and phenomenologically, we can incorporate this phenomenon, especially this uncertainty principle, by changing the algebra of our operators in quantum mechanics. Okay, and so one way of doing that is by changing the commutation relation in this form, where instead of just a constant, the commutator obtains also an operator-dependent perturbation. And so this one was proposed by Achim Kempf and Robert Mann in 95, where you have this kind of momentum squared uncertainty. But there's also many other proposals that's out there. One from 93, where this modification scales with the total energy of the system. Another one where you also have a linear perturbation, so you have a slightly different uncertainty principle that comes out of it, and many more. And so just to give you some example, if you take like typical quantum system ion in a harmonic trap, whatever you have here, this perturbation, you have a prefactor which is something like 10 to the minus 60 compared to 1, which is the quantum value. So we're talking about quadratures here. Okay, so 60 orders of magnitude smaller than the quantum value. So these are obviously, you know, very far away from possible experimental constraints. And to give you another example, if you just take typical optomechanical system, even though you operate in a different physical regime, still you're somewhere like 40 orders of magnitude away from this one if you just look naively at this commutator here. So you can assume that, you know, probably they can be negligible. And so this is why we have so many different models and speculations about what may be happening. And as of about 10 years ago, this experimental bound on this parameter was something like that, smaller than to the 33. And so this was, you know, pretty bad bound, obviously not close to the Planck scale. Yeah, okay. So what how we came about to this these models of quantum gravity was where we studied quantum optomechanics in a new regime about 10 years ago, where we looked at pulsed optomechanics. And there was the idea of doing some kind of specific quantum control sequence on the of the optomechanics to see if there's some interesting physics that one can probe with it. And so here is the following scheme that we looked at. Namely, the scheme just relies on displacement of the mechanical mirror in phase space. So if you recall, the displacement of a system is governed by the displacement operator, and that's directly related to these quadratures x and p. And so what it does, it changes the mean of a system by this amount alpha, square root alpha. And if you have two subsequent displacements, so we change the mean twice, but on top of that, we also have an overall phase, which is active on the system. Now, if one does that in a loop around phase space, what happens is that we bring the system back to its original position, but the system also gains an overall global phase. And this global phase is dependent on the area that you're enclosing in phase space. And so this is state independent, because any state, no matter with what you start, you bring back to the original position. The only difference is you imprint an overall phase. And this overall phase really arises because there is a non-commutativity between changes in position and momentum. And in fact, this is well known, and it has been proposed 20 years ago by Sørensen, Møllmer, also Jared Milburn, to use as a phase gate. Namely, if you can make the global phase a relative phase, then it, of course, has a physical significance, and this trick could be used to implement a phase gate. And in fact, this was done experimentally a few years later in the group by David Vineland. So in ion trap quantum computing, this is well known. Okay, but in our case, we wanted to exploit the fact that the commutator comes in. And so the type of setup that we had in mind is the following. I showed you already the Hamiltonian, where the mechanics in blue interacts with the light in red. Now, what we looked at that time was a different regime of optomechanics, namely the regime where it's a pulsed interaction. So if you don't have a continuous light inside the cavity, but a very short pulse, then you can neglect this free harmonic evolution. And then what you get is you get an interaction between mechanics only with one single quadrature of the system. So your unitary is just interacting between the light, number of photons, times a single mechanical quadrature, the position. And so this implements a Q&D type measurement, which is interesting in its own right, and one can use for tomography, for example. Okay, but the trick is that you can also use the free evolution after the pulsed interaction, because we know that the mechanics is harmonic. So after a while, this quadrature of the mechanics will evolve into a different quadrature. And so if you interact again at a later time, you can effectively interact with a different quadrature of the mechanical system. So if you take one and the same pulse and you make it interact, come in and out at different times, you can make it interact first with the position, then with the momentum, then with minus position, then opposite side of the momentum. So you can have 4 iterations where you really displace the mechanics in around the loop and phase space. Okay, and the point is that this does something to the mechanics or to the overall system, because you have to swap these 2 unitaries here. And swapping them, because they don't commute, actually imparts a certain effect. And in this case, we have the displacement due to the ancillary system, which is itself an interesting system, a quantum system. So if you swap that, what we get is a Kernel self-nonlinearity on the optical field. Okay, so again, the mechanics drops out, it's state independent of the mechanics, but what you see is that there is an effect on your ancillary system. So you never have to measure the mechanics, you only have to interact with it very precisely. It's a kind of a quantum control sequence, and then you can see that you have a kernel linearity on your optical field, which you can measure. Okay, but more broadly, the reason it arises is, like I said, because you have to swap these 2 unitary evolutions. And if you don't assume anything about the commutation relation between position and momentum, you can write it very generally, kind of as this more general operation. And this operation depends on the intensity of the light at different orders and different powers, as well as commutators between position and momentum and nested commutators of them. So in quantum mechanics, if this is a constant, we get this kernel linearity. But if you have alternative theory, any kind of alternative possible function of position or momentum, then you get an overall operation after these 4 loops, which is the kernel linearity plus a perturbation. But now the most important part is that this perturbation has a different power in the optical intensity. And so effectively, this different power can scale up the tiny perturbation to a higher power. So if you use many photons, you can enhance this tiny perturbation by a significant amount. Okay, so just to give you an example, one of these perturbations that I showed, one of these models of commutator deformations, had this form where it's 1 plus beta p squared. Okay, and so we can to lowest order in this parameter, which is comparing kind of the momentum of the mechanics compared to the Planck momentum squared, which just comes in, and this is much smaller than 1, of course. So expanding in this parameter, we can see how this operator looks like just by doing the algebra. And then what comes out is that you have the self-kernel linearity, as I mentioned, plus you have some more complicated operation which entangles mechanics and position. But if you have many, many photons, then the main part is that you have the highest order effect, which is n squared, n to the 4. So you get an additional perturbation, which scales to the 4th power of the intensity, as opposed to the 2nd power of the intensity. Okay, and then you can distinguish these 2 effects by looking just simply at the phase shift of the light. So this is the simplest measurement that you can do on the light. If you have an initial optical field and you look at the phase shift of the field, then you get a quantum mechanical value. So due to the self-kernel linearity, you get some phase shift on top of other effects. But then you get also now an anomalous phase shift due to this additional higher order nonlinearity induced by the different non-commutativity of position momentum. So again, you never measure the mechanics, you only measure your ancillary system. And in this case, the phase, which is very precisely measurable, and you look at an anomalous phase shift. Okay, and then one can compute what this anomalous phase shifts look like for the different system parameters. And it's completely different for different models, obviously. And so these are just 3 different commutator models that we picked out. And you can look at the numbers that come out. And in particular, we have a proposed experimental setup in collaboration with Markus Aspelmeier and Michael Venner, which developed this type of setup, at least in theory, which allows you to have one and the same optical pulse interact with the system 4 times. So it's very challenging to implement, but in principle, the idea is that you also use polarization to control when you're interacting with the system. So you have an optical pulse that interacts with your mechanical resonator, and as it comes out, you have here like a shifter of the polarization. Then you have a delay line, where you delay for precisely a quarter mechanical period, such that when it comes back in, it interacts with the momentum of the system. And you do that 3 times in a row. And then at the 4th time, you have this electro-optical modulator, which changes your which usually changes your polarization, such as it goes through this polarizing beam splitter, and the last loop, it doesn't change it, and then the light goes in the other port of the beam splitter where you can do interferometric measurement. And so this is a way to implement, because you have to have one and the same light accumulate the phase shift. Okay, and then you can look at these different models. You can look at the numbers. You can take into account all kinds of different noise sources that may affect it. Optical loss, dynamics, that there is some free dynamics still. You maybe not perfectly interacting at the right times. You still have external environment of the mechanics and so forth. So you have many different effects, and you can look at what needed to mitigate them. And so you get extremely difficult, but in principle possible parameter ranges, such as very high finesse cavities, low mass oscillators, very low frequency oscillators, which is challenging, extremely high intensity, but this is still possible. 10 to the 8 photons is not, it's nothing that special for a laser, low bath temperatures and so forth. So one of the big problems is also optical loss in these fibers, delay lines. It has to be very low. And so still, with these parameters, what we showed is that you can constrain these models to very high precision. So you can really probe these anomalous phase shifts, which correspond to these parameters, to be on the order of 1, which is where precisely you would expect some plug physics to kick in. And so, it was surprising to show that you can actually constrain it, even if it's very challenging. Still, it's within the realm of possible experiments. But most importantly, what our main motivation, really, at least mine, was to show that optomechanics is versatile also for testing different aspects of quantum gravity. And so at that time, it was mostly the focus on collapse theories. And so here we show that there is a completely different class of models, which also stems from some quantum gravity considerations, where optomechanics is also well suited to put some constraints under some parameters. And so this was, I would say, the main motivation. And since then, there's also many other different proposals and ideas what type of different things one can do with these beautiful systems. Okay, now let me just the last 5 minutes talk about some challenges about this proposal. So one is, of course, technical challenges. So there's some noise sources I'm taking into account, but others are more difficult, so like mechanical nonlinearities, because they imprint very similar perturbations on the system. Okay, and classical experiments are limited by these nonlinearities. And so it's hard to actually push it down to these numbers that we need. So there are some ideas. Maybe you can modify loops to cancel some nonlinearities, and that was proposed by Martin Plenio and his student. And you can maybe also turn it around and actually use such a system in order to do high precision metrology of nonlinearities. But there's even more interestingly a conceptual, of course, issue, which we also actually in length discuss in our original paper, mainly in the appendix. Namely, you have to specify how you're reading these models. So there's some intrinsic ambiguity in these models, similarly to nearly all proposals that modify physics. Like I mentioned in Penrose's model, there's an ambiguity about whether the mass is concentrated. And so here there's also a conceptual problem, namely that something we're used to in quantum mechanics no longer holds. And that is that there's a difference if we modify the commutator of the individual particles, or if you modify the commutator of the overall system of interest, the center of mass mode. And so depending on where you're applying your fundamental modification, the commutators of the other system will be different. And so it's not universal how these commutators are actually applied. And it's ambiguous in the theory because it doesn't tell us where, at what scale, or at what systems this commutators need to be changed. And so what we assumed here is that it's the commutator of the center of mass that is changed, because this is the physical system of interest, which is actually accessible. And that's the wave function that we are probing. And one can have a different speculation that maybe only elementary particles are affected. And if that's the case, then the signal is weaker in such an experiment, because we're talking about a system consisting of many particles. And so there's also another question, is that can we maybe have classical signatures? Do we need quantum systems? And we can do that if you do an additional speculation, namely that the correspondence between commutator and Poisson bracket also holds for these modified systems. And if that's also something that we postulate, then one can show that classical celestial mechanics and also some other classical systems already constrain these models on a classical level as well. And so there's a recent paper on that here with interesting insights. Okay, and so in other words, so there's different kind of parameter aspects of this theory, not just kind of even given one model, not just one parameter, but there's a different type of a little bit interpretation and maybe more multidimensional parameter space that one can look at. And so one also aspect is that maybe we want to really make sure that we have a quantum system, and so we have to look at signatures which are purely quantum mechanical. This is something we looked at also, okay, now this is was 5 years ago with 2 students of Myungshik. Okay, and another idea, but I think I'm running out of time, I just very briefly mention is another idea is to overcome some technical noises to enhance the signal here, namely by using many loops. So you coherently sum not just only 4 interactions, but many of them. And if you can do that, you actually get an improvement in some signal to noise for very specific noise sources. And so this is just simply to mention some noise sources you don't gain, other noise sources you can gain because you coherently enhance the signal if you use many loops. And so we looked at that. And then we also looked at maybe certain ways to mitigate some noise sources by using some clever loops, changing the direction in which we are kind of changing position and momentum, and that allows you to avoid some of the technical problems which may arise. And this just to show that there is some room for these tricks. And also, like I mentioned, Martin Planey with a student looked at a similar thing for other type of noise sources as well. Okay, and now finally, just in the last slide, I want to mention, I think, maybe the most interesting part of this proposal, which is actual experiments. And so I think shortly after we had this proposal, people who worked on gravitational wave detection with bar detectors, aluminum bar detectors, realized that actually their systems could be very well suited to put constraints on that. So not the type of optomechanical systems I talked about now, which can have this quantum control, but really systems that they use in order to detect very faint gravitational wave signals. And what they showed is that, well, if you look at the energy levels of the system in the presence of commutator deformation, they will also actually change. And by looking at how much this change is constrained with these systems, they could immediately place a bound on this beta naught, which is comparable to the bounds that were obtained at that time previously, so without even doing any additional experiments. And since then, I think the same group and the collaboration has improved these type of systems by engineering special systems where it can look at these anomalous behaviors, effective nonlinearities induced by commutation deformation. And if you know you don't have nonlinearities in the system otherwise, you can constrain these models under this specific assumption of center of mass and some classical changes of your or in this mass range changes of your deformation, then you can see that the amplitudes of your resonators change and also the frequencies. And from that, by engineering different devices, they could measure actually a much better bound of this beta naught. And I think the most recent experiment is by the group of Mike Tobar and also Pavel Bushev, where they had this very beautiful sapphire resonator, which has a very high Q factor. And they had, I think, so far the best bound for this engineered specific type of experiment geared towards testing these models in this mass scale. But as I mentioned, these are still classical experiments, so there's no quantum signature. And we also know there is actually stringent bounds from classical dynamics, also from other considerations as well, if we map the Poisson bracket to the commutator. And there was also a recent paper showing that and suggesting an additional parameter we can introduce to constrain. And there's also an older paper, very nice one, that showed that, if you look at celestial mechanics, it's very strongly constrained. So these models have some intrinsic ambiguity, but it's very interesting that we can have experimental input and then, see how they are constrained in different interpretations. Okay, and so with that, I just want to briefly summarize. So in this talk, I just wanted to give a little bit of flair and a bit of a selected flair based on kind of my own research results over the years, but just to show the very exciting aspect of optomechanics. And it stems from, testing unitarity of quantum mechanics, high precision tools for gravitational wave detection, over to test of some speculative models of quantum gravity. And of course, we know also now from the beautiful proposals that we can test even non-speculative models of quantum gravity in the linearized regime, Newtonian regime. These are the Bose and Vedral proposals. So there's a lot of different exciting physics one can probe, and it's also very exciting theoretically because there's still a lot of very interesting questions one can address. And so it allows you to test the interplay between low energy quantum physics and gravity. And there's many, many interesting and exciting directions. And so optomechanics specifically are well suited. They're high mass. We can control them very well. And for example, in this commutative deformation, the mass didn't actually enter. It was just the fact that we can control the systems in such a way to enhance the signal through a kind of quantum control sequence, which was well geared. And so, this is the example I focused on mostly to show how commutative deformations can be probed. And finally, this optomechanical experiment is really, like I mentioned, based on enhancing the signal and crucially swapping it onto an ancilla, which we can measure with very high precision. In this case, the light. So light, if you can measure the light or frequency, these are probably the best things you can do. And there are some experiments that are probed, some are in planning, and most exciting it will be to see it in a quantum regime. And so that's still challenging, but hopefully one day. And then finally, there's variations of the scheme in order to test different parameter agents, but also different type of interpretations of these models and how they might come about. Okay, and with that, I want to also, thank, of course, not only the audience, but also my collaborators on these different projects, especially Myungshik and Michael and Marcos and Chasta, with whom we developed any of these ideas a while ago. Also Sari and Pascal on the modifications with the many loop case, and then Swati, Laura, and Keith for the collaboration on gravitational wave detection. And so with that, thank you very much, and I'm happy to take any questions.
Thank you very much, Igor, for your wonderful talk. We have one question from Hori. Would you like to raise your question, Hori?
Yes, thank you very much for this very, very interesting talk, actually, and understandable for non-experimentalists. I had just one comment that I wrote in the chat. You talked about this modification of propagation, or in another way, the uncertainty relation. I wanted to say that there is a constraint from cosmological observation of gamma ray burst, and but it is for the linear modification. Therefore, my question was that the numbers that you have given in the very last part of your talk on the constant on the beta 0, are they for linear modification or quadratic?
It's an excellent question and remark. Yes, you're right. So there are several constraints also from other experiments, and one, I don't even recall what kind of assumptions go in there, whether you need classical physics or they come straight from some kind of quantum dynamics. So it's true that the linear one, I think, is better constrained, and it has some different behavior. And so the linear one is the one that I here characterize with this gamma. So the gamma 0 would be a constraint to this linear deformation, whereas this beta 1 is one where there's no linear deformation and only a quadratic one. So the beta 1 is the hardest to constrain, and the gamma 1 is a little bit easier. And you're right that there's also other types of ideas and experiments that can put bounds on it under some assumptions. So the one I mentioned in the last part on the experiments are just the beta constraints, not the gamma constraints. So actually, I don't know how the gamma constraints compare between these experiments here performed in the lab and the astrophysical observations. It's a good question. But these are the beta constraints.
Yeah, because astronomical observations are given mostly as a function of at which mass scale you expect a modification, and it is somehow a few times Planck mass.
Right.
It is not. It is not. It is not a dimensionless like beta 0 that you have given in your formulation.
Right. So there is a there is a mapping here. The dimensional S1. It's usually the it's usually the gamma that, as you mentioned, which is dimensionful, normalized to this kind of harmonic oscillator typical scale. So we just use this dimensional one with a sub-index 0. Okay, I don't have it for the gamma, but so usually it's this beta gamma. So usually it's kind of this beta here.
Yes.
And similarly gamma, and they're related by this harmonic oscillator characteristic momentum.
Okay.
So.
Yeah, therefore, it depends on really the value of omega m and m and so on.
Exactly.
The details of the instrument and
right.
experiment.
Right.
Yeah. Okay. Thank you very much.
Thank you. Other questions?
Maybe I ask something.
Oh yes, Batu.
Hi, Igor. Very nice talk. Very interesting talk. Yeah. So maybe I have one question from each of from two of the parts. Okay. So firstly, maybe this it's a general question. This gravitational detector. So can you tell me what is the main technological advance since Weber's time here? What is the main technological advance that you are exploiting here? Is it the high quality or lower size cooling?
Yeah, it's right. It's low loss effectively. So it's lower size and low loss. So the main idea of these baryons is really very simple. You just need a resonator. You just need a resonator with high Q and low loss. So you just need to measure your phonons that are reduced. And it's very few, it's very weak signal. And so, the original detectors, they actually detected some things, but I think people until today don't believe that it was gravitational waves. And so it's, they're hard to engineer and you don't know, they're very large and so forth. So you need high masses also to couple. And so the difference here is, even though you have low mass, so you kind of lose, but you have, you have very, very little loss. So you have this extremely high Q factor. And so that accounts for it. So that in some sense cancels. And so really, I think, that's the main difference, that you have high Q resonator and of course, very precise readout through microwave, looking at phase shifts of the microwave. But having said that, this is projected into what they hope to achieve, and they have experiments. They excited and they measure very high Q factors. I think actually 10 to I'm not sure 10 to the 7 or something like that they measure, but this is still not something that kind of exists. But
okay.
But that's projected what you could do with these helium type of bar detectors.
Right. And the transduction is through microwaves.
Yeah, exactly. Okay. I had this rather technical figure here. I mean, okay, but it's pretty it's too technical for me as well. But and by the way, just to mention, I think that was so. I'm a theorist as well. I'm not an experimentalist, just in case for the audience. So my knowledge of experiments are also kind of limited. But you use this resonator. As part of an LC circuit of microwaves, and okay, there's different stages that they know how to do it, but the idea is exactly that you just measure the phase shift of the microwaves as the dielectric is changing inside.
Thank you. And regarding the commutators, so you give these 4 pulses, right? So they all have to be within the cavity decay period, like faster than the cavity kappa, or
yes. So this is actually in a bad cavity limit, in a sense. So because we're looking at pulsed optomechanics, I think I only skimmed it briefly through. So it's a different regime than the usual optomechanics of the resolve sideband. Namely, so we want the pulse to be pretty short, and we want kind of a relatively large decay time. So kappa, 1/4 kappa on the order of this tau, such that the pulse kind of goes in and out. But at the same time, we still want a high finesse cavity, because this coupling still depends on the finesse. So it's the finesse. So you need a short cavity in order to make a finesse high. If you have this, if you have this kappa, so you have a large window for your system, but a very short cavity. And so engineering such cavity is still challenging, but possible. I think Michael Venner works on this. And then you get a high finesse, so you get a strong coupling while still being in the kind of so-called bad cavity limit. And only then do you get kind of, this instantaneous snapshot of a single quadrature.
Right. Okay.
And I think going back to the introduction of Myungshik, I don't even remember if that was what we discussed, but I think when we first met, this was the direction that we discussed about using pulsed optomechanics in a bad cavity limit and what kind of interesting physics you could do there. So it's kind of
very nice, very interesting.
Thank you.
Right. There's a, just in case there's the reference here from a while ago.
Yeah.
Anybody has other questions? Igor, I have one question, not regarding your work, but you mentioned. Oh, also you also worked on that. The gravity-induced collapse, and Penrose. If I remember, I mean, if I understand it correctly, says that his collapse model is different from stochastic noise model, and so that non-interferometric test is not necessarily the best one to test his own theory. So do you have any comment on that?
Yeah, that is my reading as well of his papers. I mean, obviously he speaks much better for himself, but that is my reading from how he talks about the problem. There's a difference, and that I wanted to highlight here briefly, which is Penrose argues very conceptually about the problem. So he doesn't actually have a very specific, say, mathematical model that gives you this dynamics. I think he wants to point out that there is a conceptual problem with having superpositions that induce a different kind of time-like killing vector that is measurably different. And so his postulate then is that, well, there is some kind of intrinsic problem that happens to the unitarity. It's often linked as a so-called Penrose-Diósi model to a very specific proposal, mathematical proposal by Diósi, Lajos Diósi, a very clever one, which is an open system model. So you have a completely positive map of a state to something else, and then this map replaces it's the correct evolution without even having any open system, but it's kind of postulated to be the fundamental dynamics. And it's this open system, completely positive map model, which induces also other side effects. So it induces heating, diffusion, and all the things that come about whenever we talk about within the framework kind of quantum theory, even though the motivation is that it's not coming from an environment, but is fundamental. But I think in Penrose's model, that's already an assumption, kind of. So I think Penrose's model per se is just simply that unitarity breaks down, and he doesn't actually propose a very specific mathematical formulation how that comes about dynamically, more that there is an issue. So I think I would strongly agree with the statement that testing one doesn't necessarily rule out the other. It's kind of, it makes sense that they're linked or similar, but it logically it could be different type of proposals and mathematical structures.
Yeah. Okay. Yeah. Thank you. Other questions? Well,
there's one.
Oh.
The screen tells me, yeah, Wolfgang Löffler.
Okay.
Hey.
Right.
Thanks a lot. I would have a question. It appears to me that you think there must happen something. So Ein selection, collapse, so wave function collapse. So could you comment on approaches that probably this all doesn't need to happen? So somewhere in between Deutsch and emergence of gravity in modern theories?
Yeah, oh, excellent question. And thank you very much for this remark. So I didn't want to make the impression that I believe that there's some modification or something. So in fact, my personal view is I try to be relatively agnostic, and coming from a quantum information community and being raised in Vienna, I think I lean much more towards that, quantum mechanics remain valid and these modifications will not take place, but I think it's exciting to probe them. But this is why I also wanted to make this difference between, okay, so these videos here are blocking. This difference between, let's say, the quantum character, so just testing, does quantum mechanics, is it valid on its own right, without any kind of models that we constrain, just to see how far can we push unitarity or some Bell inequality violation, entanglement. We actually had a recent paper also with Myungshik and Michael on showing that you can probe entanglement with these microscopic systems without a motivation to test some speculative model, just to kind of see that quantum mechanics is really valid in these regimes. And then there's the other part, which is, okay, there's actually some concrete proposals that one can constrain. And maybe this is how physics works, but I think most likely the case is that quantum mechanics will prevail, at least from my personal viewpoint. And so, for example, this test of quantized gravity by Myungshik, Sugato, Vlatko, and others, actually, does not assume anything different from quantum mechanics than what we know today. And so this is something that I think very likely is what we should see, although we have never seen anything like quantized gravity. So this would be, extremely exciting, but there's no good reason to believe that this should not be the case, which is a good thing. So I think it's actually a good thing to confirm rather than test some speculative things. But since we have them, it's also good to test them as well. So I think there's a range of things that we can do also without speculative models, just push forward. And Myungshik mentioned, for example, this other direction that I've been involved with on testing how time dilation affects systems. That's also something where you push into the GR regime, where you have to take into account some GR effects, and they change some quantum dynamics, but it's not speculative in any way. There's no free parameters. It's just about novel effects that arise once you kind of go beyond the typical framework of kind of non-relativistic and Newtonian physics.
Mm-hmm. Yeah, thanks a lot. I also think that all these experiments and these efforts, they are certainly worth it, independent in a way of what theory will in the end be correct. And I'm also supporting, I know, only quantum mechanics. So
right.
Thanks a lot.
So yeah, I think it's the same idea. I think it's nice to be agnostic and just kind of let them experiments talk for themselves.
Yeah.
Okay. I think in the interest of time, we should stop here. Thank you very much, Igor, for your wonderful talk, and all the audience to stay with us for 1 hour and 20 minutes. Thank you. Thank you, Igor.
Thank you.
Thank you. Bye.
Bye. Thank you very much.
Thank you. And if Igor, if you could just stay on for a minute, and Myungshik, we would like to thank you in person. Thanks everyone for coming.
Sorry, my headphones just switched off. Sorry, Sophia, were you saying something?